everyone, so we're doing now chapter 5, which is our last chapter for the Chem final, and this chapter finally has some explanations, even though most of which we have already taken, but it's fine. And sorry for the past two videos. I was recording in portrait mode. I genuinely did not realize, and I keep forgetting that when I record in portrait the video gets uploaded in portrait. But I hope it shouldn't be that much of a struggle to watch. Really sorry again. This video is gonna be normal and horizontal. Anyways, let's begin. So we start off with a definition of Avogadro's law. We already took this definition before in grade 9, which states that at the same temperature and pressure, the equal volume of gas has the same number of particles. And we know already, I don't know if this is mentioned here or not, in 1 mole, we have Avogadro's number of particles, which is 6.023 times 10 power 23. That many particles in 1 mole. So here we have a CQD. In half a mole of O2 at a particular temperature and pressure has a volume of 400 centimeter cubed. What volume will be occupied by 1 mole of H2 at the same conditions? Now, what does the law state? At the same temperature and pressure, equal volumes. So since we have moles 1, moles 2, and volume 1, so equal volumes of gases under the same temperature and pressure will have the exact same number of particles, because V1 over N1 equals V2 over N2. So here we have V1, which is 400 over 0.5 equals V2, which we need to find, over 1. So 800, because you need to double it. Boyle's law. Okay, yeah, Boyle's law. We already took Boyle's law, Charles' law, and the pressure law in physics, but now we're bringing it to chemistry. Boyle's law is when you have a fixed temperature, same mass at the fixed temperature, which is P1 equals V1. P1 V1 equals P2 V2. Now let's move on to CQD1. Some oxygen gas at room temperature and 1 atmosphere of pressure was compressed from 400 centimeters to 500 centimeters. Assuming the temperature remains constant, calculate the new pressure. We said P1 V1 equals P2 V2. So P1 was 1 atmosphere, V1 was 400, equals P2 V2. V2 was 50, right? 400 to 50, yeah. So what is it? It's 8 atmosphere. Simple math. Now we have Charles' law. Charles' law is where you have the same pressure. All of them for a fixed mass, by the way. But the only thing that changes is pressure, volume, temperature. So in the Charles' law, it's V1 over T1 equals V2 over T2. A sample of oxygen gas at 25 degrees Celsius and 1 atmosphere had a volume of 400. The gas was cooled to negative 25. So the pressure remains constant. So we know it's Charles' law. Calculate the new volume. So we said it went from, our volume 1 was 400 over 25 Celsius. But you have to take it in Kelvin. You cannot take it in Celsius if I'm not wrong. I think you have to take it in Kelvin. So plus 273 gives you 298 equals V2 over negative 25 plus 273 is 248. Cross multiply on your calculator. V2 is gonna be 333 centimeters cubed. The equation of state is the general equation. Here they didn't give us the last equation, which is P1 over V1, P1 over T1 gives you P2 over V2. We took it in physics though. The equation of state is PV equals nRT, and R is 22.4 over 273 or 24.2 over 298. I don't know why last year, or they're probably the same, but we used to also say that R is equal to 0.082 or 0.080. Depends on what they give us. So calculate the volume that will be occupied by this many moles of oxygen at this temperature, but you need to make it into Kelvin, which is going to be 300, by the way, and 1 atmosphere, and they gave you R. So volume, because it's PV equals nRT, so volume equals nRT over V. Now N was 0.5, R was 0.08 as it was given, and T was 300 all over the volume, which is 1. That's gonna give you 12 liters. Now let's move on to the next one. By the way, whenever you're using this equation, everything must be in scientific, like SI units. So this has to be in atmospheres, and this has to be in Kelvin, this has to be in moles, volume has to be in liters, and yeah, we mentioned them all. R doesn't have a SI unit. Now calculate the mass of hydrogen that will occupy a volume of 2,500 centimeter cubed at 27 degrees Celsius. So we're gonna do the exact same thing, except here they want the mass. Now what's the difference? PV equals nRT, right? But we don't want N. We know that M is equal to M over M. Small m, RT over M. And they want mass. So mass is, by the way, to get mass, you need to divide by RT. You need to multiply. No, you need to divide by or multiply by M, big M, over RT to get rid of them. So here you're multiplying by M, RT. So then you get rid of RT with RT. You'll be left with M equals PV M over RT. So PV M over RT. So what's P? Pressure is 1 atmosphere. And molar mass of hydrogen is 2 because it's H2. So 2 times 1 times volume, which is 2.5, because you need to be in liters, all over RT. R is 0.08 as given. T is 300 because it's 27. You need to convert it to Kelvin. You get 0.21 grams. Now, how many molecules of CH4 are present in a cylinder of volume 200 centimeter cubed at 27 and 380 millimeter Hg? Now, millimeter Hg means, I forgot exactly what's the unit we need to divide by to get it in atmosphere, but I'll remember like now in a bit. Anyways, so how many molecules? They want molecules. Well, you know, molecules is Avogadro's number, Na, which is 6.02, they used it here, times 10 power 23, times N, times the moles. Now we need to get the moles. To get the moles, equals PV over RT. Since it's equal to PV over RT, we just substitute in all the numbers. And yeah, like I said, it's not 380. I think, yeah, to get from millimeter Hg to what's it called, atmosphere, you divide by 760. So divide by 760 gives you 0.5. Anyways, pressure, which is 0.5 atmosphere, times volume, which is 0.2 liters, over R, which is a constant, and temperature, which is 300, should give you this number. Then you multiply this number by this number, and you get 2.5 times 10 power 21. because number of molecules equals Avogadro's number times moles. Now, a fixed mass of gas at 0 degrees Celsius, which is 273 degrees Kelvin, exerts a pressure of 0.2 atmosphere. What will the pressure become if it's heated to 27 at a fixed volume? Now, we can use always, wait, what's changing? Temperature changed, new pressure. Okay, so it's P1 over V1 over T1, my bad, equals P2 over T2. This is what I said. It's called the... Wait, is this pressure law? No, it's not pressure law, because in pressure law, pressure stays constant. I genuinely forgot, but it's here. We could use PV equals nRT, of course, and cancel what we don't need. We don't need R, we don't need N, we don't need V. We need P and T. So P1 over T1 equals P2 over T2. And you get 0.2 over 273 equals P2 over 300. P2 equals 0.22 atmosphere. Moving on. By the way, this entire video is going to be just me solving CQDs and exercises that show up on the way. Because like I said, these entire chapters for the exam on Monday are going to be pure solving. Nothing to understand, I think. I think there's some explanation down somewhere. This is a question. But yeah, I think there's something to be explained down here, like these. But most of it's going to be solving. Because there's very long questions, like this one, that need a page to solve. But listen, I doubt they're going to bring it, because there's not going to be a written part in our exam. But anyways, let's go back up to where we were. Did we finish this page? No. Oh yeah, here we reached. The temperature of a fixed mass of volume 100 centimeter cubed was dropped from 127 to 27. The pressure changed from 2 atmosphere to 1.5. What will the new volume of the gas be? So what do we not need here? We don't need, so you do PV, you write down your equation. PV equals nRT. And you cancel what we don't need. We don't need N, we don't need R. You have PV equals T. What does this mean? It means P1 V1 over T1 gives you P2 V2 over T2. And again, you're just going to substitute all the values you have into your equation and get your answer. Like I said, I genuinely can't really explain because it's all solving. So you have a sample that has 2 grams of a gas, occupies 900 milliliters at STP, standard temperature and pressure. What is the molecular mass of the gas? Now we have a formula that I don't think they used here. Yeah. Now our molar mass occupies 22.4 liters. Why? Because STP is 22.4 for each mole. Now we have 2 grams. It occupies 0.900 liters. And we know that molar mass is, you need to cross multiply, of course, to find the molar mass. So 2 grams times 22.4 divided 0.9 gives you the molar mass. And that is it. It's like you're doing RRGR. So now that we have the molar mass, oh no, that's it. You could do it in the other way, but obviously I prefer the first way. It's way easier. Now, what's the volume of 1.6 grams of oxygen at STP, which is 22.4? Now, at STP, 1.6 grams, we need the volume. So V equals mRT over MP. Substitute all your values, we get the volume. Moving on. Wait, just let me, okay. A sample containing 3.2 grams of an ideal gas will exert a pressure of 12.8 atmosphere when placed in a 500 centimeter cubed vessel at 127 Celsius. Calculate the molar mass. Guys, I think you should just like memorize formulas and like substitute the values. I'm gonna skip this because it's the exact same thing. Nothing new. Let's see the next one. 6 grams of a gas exerts a pressure of 0.2 atmosphere. What extra mass should be increased to the pressure? What mass should be added to increase the pressure to 0.8, keeping all other values constant? So we know the equation. PV equals M over M RT. Now we don't need M, we don't need R, we don't need T, we don't need, this is V, my bad. We don't need V. So it's P1 over M equals, M1 over P1 equals M2 over P2. Or the opposite, guys, it doesn't matter. So 6 grams over 0.2 atmosphere equals something grams over 280. You're gonna get 24. But they didn't ask for what's the mass, second mass. They asked how many grams do you need to add. So be careful, this is a trick that could get students very easily. 24 grams minus 6 grams to get how much you added. Moving on. A gas was heated, but by what percentage do you expect its pressure to increase? Now, we know that P2 over P1 equals T2 over T1. This is gonna give you a ratio. So, yeah, let's solve. But wait, this thing isn't getting out of my screen. Okay, a gas was heated with 100 degrees increase. So, wait, where was P1, T1 given? Oh yeah. Since P1 over T1 are constant, they're both gonna be equal to 300. And these are both gonna equal 400. So your constant is gonna be 400 over 300, which is 1.33. I have absolutely no clue how that became an increase in a 33% increase. Wait, let me check. Now, I don't know how they did it like this, but what I would have done is 400 minus 300 over 300. Final minus initial over initial. And then you'd get times 100. And I think we should be getting the same exact answer. Let me just check really quick. 100 divided by 300 gives you 0.3333. Times 100 is 33%. So that's how I would have solved it. I have no clue what they did here. But this is how I would solve it and you'd get the same answer. Anyways, moving on to the next question. At what temperature will 1 gram of H2 gas at 5 atmosphere occupy 22.4? So you want it to occupy 22.4 and you need to find what temperature. So you're just going to substitute everything other than the temperature and get a temperature. This entire quiz or this entire notes, I'm just gonna be saying substitute the numbers in, because literally that's all you can do. There's no solving included. What pressure does 4.5 grams of O2 exert in 22.4? Same exact thing, except find NO2. Yeah, you have to find the moles or you could use the other equation. Both work. You could use the equation with mass. Both are gonna work the exact same. But find the moles by dividing by 32 because it's O2. You get the moles. Then you can find the temperature by adding 273. And then substitute the numbers into the equation because, yeah, that's all you could do, honestly. By the way, you're gonna say, why is it sometimes 0.080 and why is it sometimes 0.0821? Guys, it doesn't matter. They're gonna give it to us as given in the exam what we should use as the value for each question. Moving on. So 0.2 moles of La2CO3 were placed in a 4-liter vessel. The sample was heated and decomposed into La2O3 and CO2. What will the pressure in the vessel be at the end of the reaction if it was cooled down to 0 degrees Celsius? Now, we have 0.2 moles of this. Wait. Yeah. So 0.2 moles of this. And it's a 4-liter vessel. They're asking for pressure. They gave us the moles, the temperature, and the volume. Now, we need to find the moles of CO2 produced by writing your equation, LaCO3, because they gave us the products. You have to just write a balanced equation. You're going to find that this is 3 moles. You're going to cross multiply. You're going to get the moles of CO2, which is this. And then you're going to find by the way, you're going to ask, why didn't we find the pressure or molar mass of this? It's a solid. You can't find the pressure of solids. So the only gas here is 3CO2. That's why we find the molar mass of CO2. Or we find the moles of CO2, my bad. So now you do the exact same thing. P equals nRT over V. You get 3.4. Now next question. 0.02 moles of NH4NO3 were heated in a 1-liter rigid vessel. What will the pressure be at this many temperature? And they gave you the reaction. Is it just the exact same thing? Guys, it's the exact same thing. You find for both gases, you add them together. Like here, there's supposed to be a plus sign. You add them together, put them into your equation. Exact same steps. These questions have absolutely no, I forgot the word. No new ideas in them. Now here we have a new equation. PM equals DRT. So PM equals DRT. New equation we need to know. We've never taken this one before. Finally. PM equals DRT. So what's the density of CH4 at this many Celsius and this atmosphere? Substitute the reaction. So you need density equals PM over RT. I don't know why they used the M over M. They gave us, because you need to use molar mass. So M RT over M PV. Except there's no N here, wait. Okay, my bad guys, because I got confused, because I don't have absolutely no idea why they put all the equations. We only need PM equals DRT. So D equals PM over RT. That's it. P is 5. M is C, which is 12, 16. R is 0.08. T is 373. And that's equal to 2.7 grams per decimeter. That's it. I have absolutely no idea what they put there. And now we have a question, very tall one. Anyways, let's see what's about. Now question says, a student was assigned the task of determining the molar mass of an unknown gas. The student measured the mass of a sealed 1686 milliliter rigid flask that contained dry air. Student then flushed the flask with an unknown gas, resealed it, and measured the mass again. Both the air and the unknown gas were 23 degrees Celsius and 750 torr. What is torr? I will find out now, wait. Okay, so torr turns out to be another type of measurement that is 1 torr equals to 1 millimeter Hg. So this is 750 millimeters Hg, which, by the way, to convert to atmosphere, you need to divide by 760. So the volume of the sealed flask is 1686. The mass of the sealed flask and the dry air is this. And unknown gas, the mass of it with the sealed flask is this. Calculate the mass in grams of the dry air that was in the sealed flask. Now, calculate the mass in grams of the dry air that was in the sealed flask, and the density of the dry air is this. So we know that PM why do we need PM? We don't need PM. Mass equals density times volume, which we were given both in the question. This was our mass, this was our density, and this was our volume. That's it. Very simple so far. Let's read part B. Calculate the mass in grams of the sealed flask itself. So you just do the mass of the sealed flask, or the mass of the dry air minus the mass of the sealed flask, or minus the volume, mass in grams of the sealed flask. Oh yeah, you just find they gave us the mass of the flask with the air, and we have the mass of the air itself. We found it here. So just subtract them from each other, you get your answer. So far it's very easy. Calculate the mass in grams of the unknown gas that was added to the flask. So you do this minus the answer we got in part B. Let's see. Yeah, that's exactly what I said. You do the mass of the unknown gas minus the mass we got in part B, and you get your answer. Now what's part D asking? Using the information above, calculate the volume of the molar mass of the unknown gas. Now we know that PM equals dRT, and they want the molar mass. Weren't we given density? So using the information above, calculate the molar mass of the unknown gas. After the experiment was completed, the instructor informed the student that the unknown gas was carbon dioxide. So we need to find the molar mass of said unknown gas. So you need to find the mass of the unknown gas, and we have the volume, we have the pressure, we have the time. You use PV equals nRT. Or because we want the molar mass, we use PV equals mRT over M. And since you want molar mass, it's just you replace PV and M. You get this equation. And by the way, you're gonna say, why did we do 750 divide 760? Like I said, you must use it in atmosphere. So you need to divide by 760 to make it atmospheres. And that's it. Now let's see what part they want in part E and F. Now let's focus on E. Calculate the percentage error of the... so you do the answer you got in part D minus 44 over 44. Yeah, exactly. Times 100. 39 minus 44 in absolute over 44 times 100. You get 11.4. Now what's part F? For each of the following, two possible occurrences indicate whether it by itself could have been responsible for the error in the student's experimental result. You do not need to include any calculations with your answer. For each possible occurrence, justify your answer. The flask was completely flushed with CO2 containing some sulfur dioxide impurity. Now, this occurrence could not have been responsible because the sulfur is more dense than CO2. So it would have a higher mass, not a lower mass of the unknown gas. So this is impossible. Now occurrence 2 says that the temperature of the air was 23, but the temperature of CO2 was higher. Now, if it was higher, then it would be less. So the occurrence could have been responsible, because we got a less answer. And we know that if the temperature was higher, was reported to be less than this would result in a smaller value for M, as it's in the numerator, exactly. So since it's PV equals N or M over M RT, if T increased, M would decrease, since M is in the denominator here. Since this is the case, it could be occurrence. You have to look at the equations always. So now let's see the last part. Describe the steps in the laboratory the student could use to verify the volume of the rigid flask is this. You do not need to include any calculations. Okay, yeah, exactly, that's what I was gonna say. You'd get water of a known density or liquid, I would use water, at 23 degrees Celsius, and then you measure the mass, and then subtract to find the mass of the liquid. Like you'd fill up the entire flask, subtract the mass of the liquid, and then you'd use density and then calculate the volume. Or what I could say you could also do is get a known volume of liquid, pour it, and then find out how much liquid you put, because the liquid's gonna take up the container, fill it up. Same, both work. Here they just took the masses and they used density to find the volume. Now calculate the density of CH4 at 100 degrees Celsius and 5 atmosphere. So PM equals DRT. So D equals PM over RT. I feel like I did this question a few minutes ago. Anyways, just substitute the values into your equation. Nothing hard here. Now, calculate the molar mass of the gas whose density is this at 40 degrees Celsius and 1 atmosphere. We know that, so they gave us density, they gave us temperature, they gave us pressure. PM equals DRT. M equals DRT over P. Substitute all the values, they're all given in the question. Now, something new. And we have 7 pages left. Is it 7 or? Oh no, it's 7. Let's hope they fly by. Where was I? Did that? Okay. Now the partial pressure is how much pressure a gas would exert if it was not a part of the mixture, if it was alone in a mixture of gases in the container. So how much each gas exerts, how much pressure each gas exerts is what partial pressure is. Dalton's law of partial pressure. For a mixture of gases in a container, the total pressure is equal to the sum of the partial pressure of each gas. We've taken this before in grade 9. So, if you have 5 different gases and you have each of their partial pressures, if you add all of these, they will give you the total pressure in the container. Very obvious. The mole fraction is the ratio of the number of moles to the total number of moles. Also, very obvious. We've taken it before. This is the new part. Rowlett's law. Partial pressure is equal to XAP total. Okay, now I need to figure out what they use X for. Oh yeah, I realized. X stands for the mole fraction, because C and A over N total. So the mole fraction times P total, which this isn't new, I just realized we've taken it in grade 9 also. So partial pressure equals mole fraction over times P total. Now let's move on. A sample containing 4.8 grams of CH4 and 6 grams of C2H6 are kept in one container. Total pressure was 1.2. Calculate the mole fraction of the partial pressure of each gas. To find the mole fraction, you need to find the moles. So the mass of CH4 is 4.8 and the mass is 6. To find the moles of CH4, you divide the 4.8 by the 16, which is the molar mass of CH4. And to find this, so it's 0.3 moles. And to find the same for C2H6, you do the exact same, which is 0.2. Mole fraction is gonna be, you need the mole fraction of each gas. So CH4 is gonna be 0.3 over 0.5. You're gonna say, where did we get 0.5? You have to add these two to get your total number of moles. You get 0.6 and you get 0.4. They have to continue each other, by the way. So 1 minus this must give you the other one. Now, P, the pressure of the partial pressure of CH4, we said it's mole fraction times total volume, which was given. So our mole fraction for each one times total volume. And then you could just subtract. Once we get one partial pressure, if you do total pressure minus one partial pressure, you get the partial pressure of the second one, or you could put the equation or use it again. Both ways work the exact same. Now, CQD 16 says a cylinder contains O2 and H2 at the respective partial pressure of 25 and 15. Now, what's the mole fraction of the H2 in the mixture? Now, we're given two partial pressures. If we add them, we get total pressure. And the partial pressure equals to the mole fraction times P total. So if you just do X or the of H2 equals to P total equals to PH2. I'm just doing the exact thing that's written here. PH2 over P total. Do it, you get the partial pressure. Or a mole fraction, my bad. Moving on. This chapter so far is really easy, this part. Now, CQD 17. How long is this? Anyways. So you have a rigid 8.2 liter flask containing a mixture of 2.5 moles of H2, 0.5 moles of Cl2, and sufficient argon so that the partial pressure of argon is 2 atmosphere. And the temperature is this. Calculate the total pressure. Now, to find the total pressure, we need to use PV equals nRT to find each H2 and Cl2. And that's exactly what they did here. They substitute the information given and they use the moles given and they got the pressure of each one. Now total pressure is gonna equal to these two, add to them together, plus the 2 atmosphere of argon, because the total pressure is all the partial pressures added. Moving on, the mixture in the flask is ignited by, and the reaction represented below occurs until one of the reactants is entirely consumed. Give the mole fraction of all the species in the flask at the end of the reaction. So, what we have is H2 plus Cl2 equals 2HCl. Since we already have the moles of H2 to be 2.5 and the moles of Cl2, and we have the partial pressure of argon and the temperature and the total pressure, we know that we can find the moles of argon. How? We do PV equals nRT. We already have the partial pressure, which is 2, times volume, which is 8.2. Where was this given? Wait. Where was it given? Yeah, it was given up, I'm assuming. Yeah, it was given somewhere. Yeah, then over RT, of course. You get the moles of argon. I don't know how I move the screen. Anyways, you get the argon moles. Now we can do RRGR. I don't know why they call it BBAR, but yeah. So you have 2.5 moles of H2 and we have 2 moles of, sorry guys, I had to go, but now I'm back. Anyways, so BR stands for before reaction, AR stands for after reaction. So we're gonna see, we only have 0.5 moles of Cl2. Here we have 2 Cl. So all of these moles have to be used. Before the reaction we had 2.5, 0.5 and 0.0. Since we had Cl2 and there we have 2 Cl in our final products, all of the Cl2 must have been used. So we used 0.5 moles, it's limiting. So then we're gonna see how much, so since we have 0 moles here, we're gonna have, and here we have 0 moles. So if you used 0.5 moles of Cl, and we need another 0.5 moles of H to make 1, right? So since we use 0.5 moles of H2, we're gonna be left with 2 moles of H2 and 1 mole of HCl. So now we can add the total moles. We have 2 moles of HCl, 1 mole of 2 moles of H2, 1 mole of, what's it called? 1 mole of HCl, and 0.5 moles of argon. That makes 0.350. The molar percentage molar thing of H2 is 2 over 3.5, 2 divided by the whole. This is 1 divided by the whole. This is 0.5 divided by the whole for argon. And for chlorine, it's none because we used up the entire thing. And I really need to stop clicking random things. My bad. Anyways, where were we? Wait. We didn't see this yet, so we were above this. Yeah, there we were. Like I said, no chlorine left since it was limiting, all used up. And that's how we find the XAR, XCl for everything. Now let's move on to CQD 18. 20 milliliters of neon gas was collected over water at 27 degrees Celsius. The pressure in the tube was 1.32 atmosphere. Assume that the vapor pressure of water was 27 at 27 degrees is 25 millimeter Hg, which to convert to atmosphere you divide by 760. So they're asking us to calculate the number of moles of neon. So the partial pressure of water vapor is gonna be 25 over 760, like I said. Or sorry, this isn't partial pressure, this is just pressure. It's gonna be 0.0329 atmosphere. And okay, they're telling why it's 329. The Kelvin, it's gonna be plus 273. And now the pressure in the tube is the pressure of the neon and the water vapor. We know that the pressure of the water vapor was just found, and the pressure of the neon is 1.32 as given here. And this is supposed to be a plus. They kind of got it wrong, but you get 1.29. Now then you use the equation of PV equals nRT, and you find the moles. Moles is equal to N, which is equal to RT over PV. No, it's PV equals PV over RT, my bad. So now, you use the equation, you input your numbers, you get this to 3 significant figures. Now what we do next is, we just found it. They wanted the moles of neon, right? Yeah, they just were asking for moles of neon, so you just found it. You had to find the pressure of neon. Now, it is minus. My bad, I did not realize. I thought this was pressure of neon. This is pressure of the entire... This was pressure in tube. So the pressure in neon is this minus this. It was correct. My bad, guys. So, now, we have 5 pages left, thankfully. So, equal masses of HE and NE are placed in the same vessel. Calculate the partial pressure of NE if the total pressure is 6 atmospheres. Okay, if total pressure is 6 atmosphere and there's equal masses, then, yeah. So, what we know is the total pressure is 6, and each mass, we only have one mass because they're both the same mass. So to find I totally forgot what this is called, the mole over total mole. I forgot what it's called. Anyways, to find that you need moles over total number of moles. So moles of Ne over total moles. So He plus moles of Ne. And which is the same as the mass over molar mass over mass over molar mass plus mass over molar mass. Now what you're gonna do is we're gonna assume the mass is 1 gram. Okay? Because it doesn't matter. They're all the same mass. So 1 over the molar mass of neon, which is 20, over 1 over 20 plus 1 over 4, which is the molar mass of He. Wait, He? Yeah. Then you're gonna get 1 over 6. Then you multiply it by the total pressure to get the partial pressure of Ne. 6 times 1 over 6 is 1 atmosphere. The kinetic theories of gases are that the particles are so small compared with the distances between them. So there's a bigger distance between them than the particle size, so the volume of an individual particle can be negligible. The particles are in constant motion. The collisions with the wall exert a pressure. The particles are assumed to exert no force on each other, as they are assumed to neither attract nor repel each other. The average kinetic energy of a collection of gas particles is assumed to be directly proportional to the Kelvin temperature of the gas. So kinetic energy is proportional to Kelvin temperature. Moving on. List the 4 postulates of the kinetic theory of an ideal gas. So what you have to do is just name the exact same things I named there. Memorize them, by the way, it's very important. Now, diffusion is the mixing of fluids. Effusion is the mixing of fluids through a tiny orifice or opening. Graham's law of effusion is rate of effusion of gas 1 over rate of gas 2 equals the radical of molar mass 1 over molar mass 2. Or sorry, no. You have to focus. 1 over 2, 2 over 1. You have to switch them. Ooh, this one's under radical sign. Now we're gonna solve. We took this in grade 9, by the way. But my teacher used to give us another equation, which is light over heavy equals heavy over light, but it doesn't matter. Anyways, and helium, what question starts with? Okay, and helium gases are placed in the same vessel which had a tiny pinhole. So we have effusion. The particles of which gas will on average effuse faster, and how many times faster? So we have, okay, here they were supposed to say hydrogen and helium gases are placed. So at the same temperature, we need the kinetic energy. Kinetic energy from physics we know equals half mv squared. Yeah. Oh yeah, by the way, it's helium is 4. Wait, let me look at my periodic table. Helium weighs 4 grams and so does hydrogen weigh 4 grams. So they're both weigh the same. So you could say they're equal to each other, mv squared. Now the mass of He is going to be 4 times v squared into half. Why is it 4 here? Wait. My bad, it's 4 because we cancelled the half from each side. I wasn't focusing. Equals 2v squared. I don't know why I put the 2v squared. Now, the v of the hydrogen equals to 2 radical of 2v helium. So what we do is we have 2 or 4 v helium squared equals 2 v hydrogen squared. The volume of hydrogen is equal to the volume, I mean velocity, my bad. This is velocity, not volume. I've been saying volume this entire time. Compare their speed. So the velocity of hydrogen is equal to radical 2 of the velocity of helium. And if you're gonna ask me why, it's because we moved 2 to the other side. So you divide it by 2 on this side. So divide by 2, the 4 is gonna cancel and it's gonna stay 2. And then to get rid of the square, you have to radical on both sides and you're gonna be left with, by the way, this isn't under the radical sign, it's velocity of He. So this is equal, so the velocity of H2 is equal to 1.41 of velocity of He. So the velocity of H2, hydrogen, effuses 1.41 times faster. Moving on. Okay. Now, the molecules of a certain gas X has the formula N2H2X, move 4 times as slow as the molecules of hydrogen gas under the same conditions. 4 times as slow. Let me just change the color. 4 times as slow. Now calculate the molar mass of X. So do we have the same conditions, means same temperature? We need to compare their speeds. And they're saying it's 4 times, so this is equal to 4 times the speed of hydrogen. So it's 4 times H2 speed, velocity of H2. Now calculate the molar mass. The molar mass is... Did they even calculate the molar mass here? I doubt they calculated the molar mass. They calculated it here. Oh yeah. So yeah, see, like I said, velocity of H2 is 4 times faster. Ah yeah, this one is... I put the 4 beside this one. 4 times of this is equal to H2, 4 times the speed. So velocity of H2 is given that it is 4 times this. So at the same temperature, the kinetic energy should be equal because it's at the same temperature. So if we're putting half mH2v squared equals to half mv squared, we're gonna get, cancel the halves, we're gonna get 16, because the velocity is 4 times 4v, so it's 16 mH2 equals to mnxH2. Guys, I'm sorry, I had to pause this video like a million times to figure out what was going on. But honestly, like, as much as I try to look at this, it genuinely makes absolutely no sense to me. So what I'm gonna use is the equation we've been using since grade 9. And the equation mentioned above, R1 over R2 equals radical M2 over M1. So we know that the rates, this is 4 times faster. So we know that hydrogen over H2X. So we know that H2 over H2X is equal to 4. That's the rate, like ROR. The rate is 4 because we know it's 4 times faster. So 4 equals the molar mass of the... If 4 is for hydrogen, then this must be for molar mass of N2HX, or no, NX HX, or H2X, my bad, over 2. So what we need to do is we need to square on both sides. We get rid of this, we square this, it becomes 16. 16 times 2 means that it's equal to 32. Now I know where we got this from. Now 32 is the same as N is 14. So 14x plus 2x equals to 16x equals 32. So our x is equal to 2. Now our molar mass was 32, x was 2. This is just it. This, I have absolutely no clue what's happening. And after pausing, I figured out that this was the answer to the question above it. So let's continue our video. Let's continue solving. We only have a few pages left. A 5 milliliter sample of O2 requires 50 seconds to effuse. At the same conditions, 5 milliliter of gas X requires 80 seconds. What's the molecular mass of the gas? Now we know we need to find the rate, or time of effusion, as we could say. So time of effusion is 80 and 50 seconds. So 80 and 50 seconds. 80 is for what's it called? Gas X equals the molar mass, equals radical molar mass of X, and time for O2 equals the radical of the molar mass of O2. You're gonna say, aren't we supposed to flip them? That's when we're talking about rate. In time, you don't. So radical 32 times 80 divided by 50 gives you mx which you get as 82 when you put it into your calculator. Moving on. So we have a nice question here. No, not really, but sure. Okay, so we have a question that says 5 identical balloons under the same condition contain each of the following gas: C2H6, SO2, O2, CO, and E. Which balloon contains the greatest mass of gas? So what we know is that this entire explanation about it having the same number of moles is useless, because they're saying mass, they're not saying number of particles. They all have the same number of particles, yet they don't have the same number of mass. So personally, this entire thing is actually useless, I'd say. SO2 has the greatest molar mass, so it has the greatest mass. Done. Compare the average kinetic energies of the gas molecules in the balloon. So the kinetic energy of the lightest gas is gonna be the fastest. Or wait, no, sorry, my bad. Each are under the same conditions. I forgot that part. Since they're all under the same conditions, they all have the same energy, because the kinetic energy depends on the temperature. Now, because they said also compare the average kinetic energy. They didn't ask you which one's fastest. Now, which gas is expected to deviate most from ideal behavior? It's definitely SO2, because it's the biggest, and like they said, the largest electron cloud, so strongest intermolecular forces. Usually it's the largest one that's gonna deviate the most. 6 hours after being filled, all balloons have decreased in size. Predict which balloon will be the smallest. So the lighter the gas, the faster it will effuse, because it's lightest. So NE is gonna diffuse the fastest, so NE is gonna leave its balloon the fastest, so NE is gonna be the smallest. Moving on. We have a lot of examples, then more examples, then a CQD, then an example, then another top question, and we're done. If you can't tell, I'm very much done with this quiz or this paper. Now, an ideal gas was cooled from 25 to 5 in a rigid container state, which will be affected on each of the following. Average molecular mass will have no effect, because what's the temperature going to do on the mass? Average molecular speed is going to decrease, because the more you decrease temperature, the lower the speed. Average distance is also going to decrease, because they have less kinetic energy to move. Pressure is going to decrease, because it's PV equals nRT. PV equals nRT. If T decreases, pressure decreases. Density is also going to stay the same, because it has nothing to do with temperature. Now, total kinetic energy is of course going to decrease, because you're decreasing temperature. Number of collisions is going to decrease, because you decrease the kinetic energy by decreasing temperature. Why does heating the air make it rise? It's because hot air is less dense than cold air. That's why we put radiators on the ground and we put air conditionings up, because hot air is going to rise and cold air falls. As we heat a gas, the molecules move more faster and spread further apart. It expands and the air lifts up. Under the same temperature, which gases will have a similar or effusion rate? Gases of the same molar mass are going to have similar effusion rates at the same temperature. Now, if the speed of an NH3 molecule is 500 meters per second, what is the speed of an SO2 molecule under the same temperature? Now, what's given is 500 meters per second, so we're given the rate of NH3. They want the speed of an SO2 molecule under the same temperature. Now, I'm going to also ignore everything here, and we're going to do R1 over R2 equals radical M2 over M1. So rate 1, we're going to say is 500. So M1 is going to be the molar mass of NH3, which is N is 14, and so it's 17. Now, we don't know R2, that's what we're finding. SO2, though, is going to weigh 64. Now, we could just, if you have the calc function on your calculator, do it. If you don't, you have to square both. You have to square this and make it equal to this. Then you just do 17 times 500 squared, divide 64 under radical. It's going to give you 257.69, which rounds to 258. That's it for part A. Let's move on to part B. Okay, so a sample of ammonia gas effuses at the rate of 0.01 mole per minute. Calculate the rate of effusion of each of the following gases under identical conditions. Do we have to actually do it for each of these gases? Oh, what you're just gonna do is... Oh yeah, so since we have this equation, the volume of the gas, what does volume have to do in velocity, I keep mixing it up. So the velocity of the gas is, since it's, you could cross multiply by the way, so it's velocity of gas over velocity of NH3, but what they did was they cross multiplied and they took the velocity of NH3 here. So whatever gas we want, you just fill out the equation here. So we know the velocity of NH3 is 0.01, that's given. Or yeah, the rate, same thing. So just now we know already molar mass of NH3, it's 17. Now, what you do is you replace the molar mass of the gas into this equation. So you just replace it by the molar mass. As you can see here, you put 2, here 44, here 4, here 70. You multiply it by 0.01, which is the rate, and you get your answer. Now, a glass container is filled at RTP, 24 degrees. 24 degrees, with equal number of moles H2, O2, and NO2. The gases leak out of a pinhole. After some time, some of the gases effused. List the relative values for the partial pressure of the gases remaining in the container. H2 is going to be the least because it's the lightest, then O2 is second lightest, then NO2 is the heaviest. Gases behave most ideally under really high temperature and low pressures. Just know it. Now, we're on page 48, 2 pages left, thankfully. Now, under which of the following conditions will 1 mole of a real gas behave most ideally? Now, we're gonna remove these because we need higher temperature. And so it's most likely high temperature. We need high temperature, low pressure. So this one is the answer. Which of the following gases deviates most from real behavior? The one that deviates the most is the one with the... I think it's the heaviest, wait. Yeah, SF4 is the heaviest, that's why. Why do real gases behave the most ideally? It's because they exert little force on each other, because they're very light particles and they're under high temperature, low pressures. Now, molecules of a real gas do occupy volume. Volume actually is available to a given Molecules of real gases do occupy volume. The volume actually available to a gas molecule is volume minus NB, which is P equals nRT over V minus NB. And they actually do exert forces. The observed pressure is smaller than it would have been ideally. I don't know if this needs to be memorized though. So the P of observed is P prime minus A into N divided by V over squared. So P observed would be, what's this? Okay, so what I understood is that, what you need to know, is that they do occupy volume and they do exert force. So when we write the equation PV equals nRT, this is for the most ideal gas that does not even exist. So when we're talking about real gases, we need to take into consideration this proportionality, which is the volume. It's called the volume correction, because there's no actual, like NB is the volume correction, because there's actually, it does occupy a volume. So we need to account for that volume. Now, P observed is equal to nRT over the V with the correction minus this is the pressure correction. What we need to know is this is the ideal pressure because it has the pressure correction, and this is the ideal volume because it has the volume correction, because they do exert pressure and they do have a volume. So we need to have their corrections, because then it will be more accurate. And the larger the molar mass, the more it deviates from its behavior. Under the same conditions, which of the following deviates the most? It should be the heaviest one. Honestly, I have no brain power to actually calculate the heaviest one, so whatever one's the heaviest one, that's your answer. Now, this last question, I don't understand why a question has to be 2 pages long with the answer, but let's see what's up. Now, butanol and steam react as in the equation below. The boiling point of butanol is this: when 7.65 moles of butanol are added to 20 liters in a rigid container heated to 25 degrees Celsius, some of the butanol undergoes this reaction. A system is left to reach equilibrium at this temperature and at the equilibrium amount of CO in the reaction. The vessel is found to be 5.25 moles. Wait, sorry, what? The system is left to reach equilibrium at 250 degrees Celsius and the equilibrium amount of CO in the reaction is found to be 5.25 moles. Determine the amount of moles in the of H2 in that container. So I'm assuming we just do our RGR with CO, because we know how many moles of CO we have, right? And the CO is found to be, so 5.25 mole for 8. How much? So 5.25 times 8 divided by 4 should give us 10.5 moles, yes. Now, part II is asking, find the mass of butanol remaining in the container. So what we're gonna do is, did they mention anything about limiting rate? Yeah. So the reacted, we need to do also our RGR. Same thing. Yeah. So we know that there was 5.25 moles. So 5.25 divided by 4 is gonna give us 1.3125. Wait, do we even need it? I'm assuming we do, yeah. Yeah, exactly, 1.31. Then we need to find the moles of butanol left in the equation. So we need to see how many moles did we begin with. And it was 7.65, it's right here, minus the 1.31, and we get our answer, which is 6.34. So the mass is going to be the moles times the molar mass, and that's it. Now part III. What's the mole fraction of H2 in the container, knowing the initial number of moles of H2O is 6.5 moles? Now you're going to say, what does the initial number of moles of H2O matter? It's because we need to find the total number of moles, right? So the mole fraction of H2 is we need to find the moles of H2O. What we're going to do is, we're going to do the same thing. 4 times 5.6 whatever. Are we just going to cross multiply? Oh yeah, the moles of the water reacted equals 3 times the moles of this reacted, because we have the same number of moles just times 3, because it's the same exact reaction. So you do 1.31 times 3 to get the moles of H2O, which is 2.57, I think. Yeah. So then you're going to do the total moles of hydrogen, which we got here in the part A. Then you're going to divide it by the sum of all the moles of all the compounds we have, which you're going to get to equal 0.426, and that's your answer. Now part IV. Determine the total pressure in the container at 250 degrees Celsius. I think you need to do PV on RT, don't you? Yeah, you need to do PV equals nRT. P total, which is what we're finding, equals N total, which is what we just found, or which is just the sum of all the moles. Yeah, which is just what we just found by doing this here. R is given, T is also given by 250 plus 273. all over 20, which is the volume given also. Everything was given. And you get your answer. Now, part B, the four gases that are present in the container at 250 are C4H9OH, H2O, CO, and H2. The average kinetic... Okay, they're all at the same temperature, so they all have the same average kinetic energy, don't they? The average kinetic same because they're all at the same temperature. Now, which of the following gases has the least average molecular speed? It's definitely the heaviest one, which I'm assuming is C, this one. It is... Yeah, this one because it has the most molecular mass. Now, when the rigid container is cooled to 110, it's observed small amounts of CO and H2 are dissolved in the liquid. Explain which of the following gases is more soluble at 110. CO would be more soluble because the IMF between the molecules of H2 and our London dispersion... Did we even take this? Dipole... I'm honestly not sure we took this, to be honest. So I'm just gonna read it out because I do not remember seeing this anywhere in the folder. CO would be expected to be more soluble because the IMF between molecules of H2 and C4H9OH are London dispersive forces, LDFs, and between the CO are London LDFs and dipole-dipole forces. Now, LDFs are stronger between CO molecules and C4H9OH molecules because CO has more electrons than H2, so its electron cloud is more polarized. And dipole attractions are stronger than LDFs, and CO has those. That's why it would be more soluble. And yeah, I don't know if we actually need to know this information, but sure. Now, all three identical flasks are filled separately with 1 mole of hydrogen, krypton, and nitrogen dioxide. All flasks are kept in the same room at 0 degrees Celsius. The pressure in each flask was found using the ideal gas equation, then measured using a pressure gauge. Now, after studying the data, which the following is noted: pH2 is calculated using the ideal gas law, almost identical to the one found practically. pKr is calculated by the ideal gas law, is less than the one found practically. PNO is calculated by the ideal gas law and is greater than the one found practically. Explain these observations. Now, H2 has the smallest molar mass, its volume and the IMF between its molecules are negligible. Kr is a large atom, the combined volume of the Kr is too large and to be assumed negligible. So, compared to the volume of the container. IMF forces between the NO2 molecules are relatively strong, and their combination of LDF and dipole-dipole forces, the molecules are attracted to each other and do not exert as much force as they would have if they had negligible attractions. So that's why it's almost identical H2 because it's lightest also. Kr because they said it's a big particle, it's noble gas, so you can't really count its volume as negligible. You have to calculate its error constant. And the NO2, it's dipole and NDRF forces have to affect it somehow. I will see if... I don't think we've taken this. I will be asking the people in my class, but anyways, that's it for chapter 5 and the entire periodic. Hope you understood everything. Have a great day. Bye.